Hi, I'm John Maschey, Director of Systems Technology at Silicon Graphics. I'm here today to talk about hardware, wetware, and software. Now, you may be familiar with hardware and software. You may be wondering what wetware is. Wetware is another term for human beings. Now, it originates in cyberpunk science fiction novels, but I've seen it used in The Economist and Forbes, so I think it's an acceptable term to use for us human beings. So what I'm going to talk about is, first, the very strong trends in hardware that we can expect over the next few years. Next, I'm going to talk about the very strong non-trends in humans over the next few years. And then finally, I'll end up with the kinds of software that people use to bridge the gap between the terrific increases in hardware and the terrific non-increases in human being performance. What I want to do first is remind you that I'm going to use a number of graphics here that use logarithmic scale charts rather than the more normal linear charts that most people are used to. So the chart on the left shows a logarithmic increase. It looks like a straight line. It's not very impressive, but it is the same data as the chart on the right. My marketing friends would like me to use the charts on the right because it looks more impressive, but I'm an engineer, so I use the ones on the left. Now, in the next three graphics, what I'm going to do is summarize the entire computer business in three graphics. This was encouraged by the old Journal of Irreproducible Results, which tried to get all scientific data onto 7 graphics. I'm going to do the computer business on 3. On the next graphic, we see the first strong trend. That is more. That is, things, in terms of capacity and performance, tend to grow at an exponential rate over time. This could be the number of bits per disk, per DRAM memory chip, or the performance of CPUs. Now, if that one is true, so is the next one, which is less. That means that the cost for any given amount of capacity or performance tends to go down pretty quickly over time. That brings me to the third graphic. This, of course, is the performance gain expected in us wetwares. This is not very encouraging. That is, what you see now is what you get. About the only recent improvement in human performance is the slight increment of hand-eye coordination amongst the Nintendo generation. They are very quick with those screens. They may not be able to read or write, but believe me, they are very quick. Perhaps more important, they are not afraid of computers, and they expect very interactive interfaces from the computers they use. I do believe in the long term this actually has a very serious effect on the kind of computers and the computer interfaces that we'll use. Now, to get a little more serious on the next graphic, I show the long-term trend of memory chips, and that goes through around the year 2001. This shows both DRAM and static RAM memory chips. They are increasing at the rate of 4x every 3 years. We expect this to continue to somewhere around the year 2001. After that, it's not so clear. What's the problem? Well, we've been using optical lithography for decades to build the chips. Around the year 2001, the size of transistors gets smaller than the wavelength even of deep ultraviolet light. So we will have to switch to X-rays or electron beams or something else, and the people are working on this in the R&D labs. Something is going to have to change, and it may take us a little while to adapt to that. Nevertheless, we've been on this very strong roll for years and years, and it's going to keep up for at least a few more years. Now, on the next graphic, we see how this translates into performance. We've got 3 lines on this chart. The top line is the clock rate of very large, powerful vector supercomputers, such as the Cray research machines. The middle line is the clock rate of the classic large mainframes. These both use a technology called ECL, or emitter-coupled logic, which used to be much faster in its basic switching speed compared with the CMOS technology that you find in personal computers and workstations and so forth. What's been happening is that these lines have been converging. This is why you now start to hear about CMOS mainframes and how much money they save. And you even find CMOS technology starting to be in the supercomputer business. And in fact, we think these technologies will merge out there in just a few years. Now, if you'd rather look at the delivered performance, on the next graphic, we see the peak megaflops, relevant for people who do scientific and technical computing. What we find here is that at least on the peak performance metrics, the CMOS chips have indeed been approaching the speed of the large vector supercomputers. Whether or not the actual delivered performance does that really depends on whether you can get the data in and out of the computers. We'll come back to that later to see the extent to which bandwidth is or is not keeping up with the speed of the CPUs. So what are the implications of these trends here? Well, there are a couple fundamentals in terms of the performance and capacity that you see from chips and storage technology. The first one, which drives a great deal of the chip industry, is that DRAM memory chips get 4 times larger in capacity about every 3 years. Unfortunately, the access time to DRAM does not improve anywhere near so fast. 10 or 15 years ago, the clock speed of CPUs and the access time of DRAM memories was about the same. By now, the clock speed of CPUs is substantially faster than DRAM memory. If you're not careful, you can find that the CPU is spending all of its time waiting for DRAM. That isn't doing anything useful for anyone. Now, CPUs themselves are getting about 3 or 4 times faster about every 4 years. It's less regular than the DRAM technology, which is very strongly driven by the chip technology. CPU performance has things like compiler technology and which benchmarks you happen to believe and so forth, so it's a little more complicated. Now, it used to be that disk technology used to get about 2x better about every 3 years. But in the last few years, since around 1988 or 89, it's improved to follow the same trend as DRAM chips. That is, it increases in size about 4x every 3 years. What's truly odd about this is that still no one has too much disk space. And we'll come back to that later because that's a real issue. The next issue here is that although disks are getting faster and larger, the access time to them is not improving very quickly. In fact, it's about 30% every 8 years. Because after all, that is physical motion. And for a computer designer, physical motion is evil incarnate. It's something to be avoided if there's any way possible to avoid it. You have to spin the disks and seek to find the data. This is painful because it is physical motion. Now, the last rule up here is a funny proverb of computer design, which is, money can buy bandwidth, but latency is forever. What does that mean? Well, it means that you can interleave DRAM memory chips together and get much higher bandwidth. But the access time to the first byte is still the access time to the first byte. You don't get it any earlier. The same thing happens with disks. You can use disk striping to access many disks in parallel, and you can raise your bandwidth up to fairly high levels. But the trouble is, it still takes some number of milliseconds to get that first byte of data, and that remains a problem. So now on the next graphic, let's take a look at the fundamental results that happen from these trends. The first thing is that computer designers increasingly must worry about memory hierarchy. That is, from the left, you have CPUs that are very fast, they have cache memories that are very fast, but they're not very large. They cannot hold much data. Working your way over towards the right, you get more and more storage, but the access time gets worse and worse. You may or may not get high bandwidth because you can pay for it. It's just that the latency of access is a very difficult problem to improve very much. The second thing that's happened is that CMOS microprocessors have basically taken over the bulk of the computer market, from TV sets up through supercomputers. After all, these days, television sets are microprocessor controlled, so you do see them in there. There's still a very high end of the supercomputer business that uses the ECL technology. I think in the next few years you will see CMOS used even at the very high end of the supercomputer business. The next result that's happened is that 64-bit microprocessors have actually become relevant in the last couple years. That is, there's an actual reason to buy these things. What does that mean? Well, a 32-bit microprocessor can directly address 4 billion bytes or 4 gigabytes of main memory. Now, that's more than you have on your desktop. Nevertheless, people have already been selling server machines, refrigerator-sized machines, with 6 gigabytes or even up to 16 gigabytes of physical memory. Remember, over time, the costs of memory drop, and the result is people with the same budget can afford more of it. Strangely enough, if they can buy it, they would actually like to use it. Therefore, by 1994 and 1995, people were buying refrigerator-sized machines with, in fact, 8 or 16 gigabytes of main memory. Oddly enough, some of those people were ready to use it the next day. That is, they had one Fortran program, they recompiled that program with larger arrays, they were able then to model a bigger universe or a bigger piece of the ocean, and they were happy. In fact, they complained that they couldn't buy more memory at that time. So that's the next trend that's happening here. In addition, there's one part of this that hasn't quite happened yet, but it's in progress right now in 1996. And that is, in the commercial world, people have noticed that the disks refuse to have much better access time. The fastest disk you can get is the one you do not have to access at all. So what the major database vendors are doing is reorganizing their databases so they can bring more of the pointers to data, the indices that is, into main memory and keep them there so that they can compute to decide where the disk data is, then go to disk and read the entire set of disk blocks in, avoiding series of disk accesses where you have to wait for one before you can go chase the next one. So this is actually turning out to be something that's just in time. It's when people can afford the memory, and it's right at the heart of these different trend lines. That is, that you get more disk space that you want to have, you get more memory that you want to have, but the access time doesn't improve very fast. Therefore, the way to beat the access time is not do the accesses. Now, the last thing is one called Parkinson's law, usually used in organizations. That is, an organization will expand to consume whatever budget you can give it. This also applies very strongly to software. Software will expand to fit whatever amount of memory and disk space you can pay for. Somehow, no matter what you buy, there's always something that fills it up. Now, in particular, particularly because of some of Silicon Graphics customers, we are used to this because people want to do things like keeping movies online and editing them, which is fairly complicated and actually a very large amount of storage in the form that our movie-making friends like to keep. When you do digital media, where you have libraries of audio and video and image, these can consume any amount of disk space that you can manage to pay for. This is good, speaking as a computer vendor. Okay, now let's go look at how easy it is to move the data around on the next graphic. What I've got here are 3 sets of bandwidth numbers that describe the speed at which you can move data. If you have more data, you've got to learn how to move it faster. Now, on the left column, these are all measured in megabytes a second. There are several numbers given for the memory speeds of some fairly common symmetric multiprocessor machines that have been on the market for a while. These are the numbers in the 1,000 megabytes to 3,000 megabytes per second range. That's kind of the current state of the art for classic shared memory multiprocessor machines. Now, up at the top, just to keep a sense of proportion, is an older Cray YMP C90, which does 11.5 gigabytes a second per CPU. And of course, you can have more than one CPU in a system, and you can actually add them up. There, of course, are newer Crays, like a T90, which is off the scale at 25 gigabytes per second per CPU, or 800 gigabytes a second for an entire machine. I could have put those on this chart, but I didn't feel like redrawing the chart. Supercomputers really are off the scale compared to with the systems that most people are used to. Now, that's sort of the good news. The not so good news is input-output, which is shown in the second column. still using the same megabytes per second scale. Let's start from the bottom. If you have to back up to mag tape, you're talking about several megabytes per second. If you look at a single SCSI disk of the common flavors used, you maybe get 4 megabytes per second raw transfer rate. If you go to a whole SCSI fast and wide channel, you're talking about 20 megabytes per second peak, maybe 17 megabytes per second sustained if you're good. Well, good news is Ultra SCSI is 40 megabytes per second peak, and that's starting to become available recently. Probably the most common bus you'll see here would be the PCI bus, 133 megabytes per second peak, commonly used in PCs, but also for large server machines. There's also a double speed version of that. You don't really see very much, called PCI 64. That's 266 megabytes per second. Now, in fact, we are starting to use these things, although they are no faster than the I/O bus we've been using for quite a few years in our workstations. Now, if you build a larger server machine, you'll tend to have more than one I/O channel. So in this column, I've showed a Silicon Graphics Challenge machine, which has a number of I/O channels and gets about 1.2 gigabytes per second worth of total I/O at its very best. Now, if you look at current machine designs, people are moving above these numbers for microprocessors. If you're interested in these current trends, you should perhaps take a look at the talk of UVCs done by my colleague Dan Lenoski, and he will talk about those different trends and how you can get better bandwidth than these. Now, the third column is the one that's actually pretty frightening. That is the speed of networking. Starting at the bottom, Ethernet is about a megabyte per second. That's the common 10 megabit per second Ethernet. There, of course, is a 10 times faster version of that that's starting to be used. That's 100 base T Ethernet. 100 base T, FDDI, and ATM OC3 are all in the 10 to 15 megabytes per second range. You'll notice that this is substantially less than the speed of memory inside a machine. Be warned, when you are looking at logarithmic scale charts, there are huge factors in what looks like a small space on the graphic. So what can you do to do better? Well, ATM OC12 is a 4 times faster version that would give you about 60 megabytes per second. That's not something that's very easy to buy yet, but it is coming. Although supercomputer centers often use HIPPY, which gets you 100 megabytes per second peak. Those are often used to talk between supercomputers or between supercomputers and very aggressive workstations. One hope for the future is there's a faster version of HIPPY that's actually up around 1,000 megabytes or a gigabyte per second. It's called HIPPY 6400. You'll start seeing that, I think, in 1997 or 1998. Now, if I back off from this chart, and I think to summarize it, what I see is that the bandwidths inside a computer are far higher than the bandwidths going in and out of the computer, and those bandwidths are even higher than the speed of the network infrastructure. So a thing that we've always got to watch in our computer design is we can make the CPUs go fast, we can make the memory go fast. We have to work very hard at the input, output, and networking to keep up with the speed of the machines. Otherwise, we have fast machines that are not doing anything useful. Now, on the next graphic, I add back that difficult part, that is the latency. Here what we have is vertically, we show the same bandwidths that I've been showing you before, but horizontally, we go in increasing access time. Let me start over at the right, out in the world that people are more used to. If you look at the time to exchange messages on a typical network, it's some number of milliseconds, even if the hardware is faster. Why is it milliseconds? It's because there's often layers of software protocols where a message starts with a user program, works its way through an operating system, gets onto some kind of communication medium, goes over to another machine, works its way back up through the operating system, and finally gets a few bytes to some other user program. This takes a lot of work to both cut the time down on this and still obey all the standards that are out there. Now, a real odd thing is that if you look at the different networking protocols stacked up over here at the right, you discover that you get an increase in bandwidth by spending more money. It's just that the latency doesn't really improve very much. It comes back to my old proverb. Same thing happens with disks. We illustrate here having a number of disks striped together. We can get something like 500 megabytes per second reading a single file off disk by having many of them striped together. Unfortunately, it's still some number of milliseconds to get the first byte of data. Now, quite a few vendors have been trying to take more general networks, make them a bit more specific, and use them to interconnect their multiprocessor machines. These include things like the IBM SP2 or the DEC True cluster. They are represented by these dedicated special purpose networks in the middle of the chart. As you can see, they're trying to get bandwidth that gets closer to the inside of the machines and latency that gets near them, and they're working over, but it's pretty hard. If you now look at the performance characteristics of the SMP memory systems, what you find is bandwidths in the 1,000 to 3,000 megabytes per second and latencies in the half a microsecond to microsecond range. And you can see the bubble for it there in the middle of the chart. Now, of course, that's a lot slower than CPU cycle times, so we put fast cache memories in between to the right of the SMP memory bubble there. Those have access times in the tens of nanoseconds, so we're getting better. And the CPU access to registers, by now, is down in the several nanosecond range. That's the bubble at the left. And again, just for proportion, for us microprocessor people, up at the top is an older Cray with memory access time in the 100 nanosecond or so range and up in the 11 gigabyte or so bandwidth. So, once again, I remind you that you have to worry both about bandwidth and latency. One of the worst sets of disasters I've seen in computer applications is when people think that by increasing the bandwidth of their network, they have solved all the problems. In many cases, what counts is not the bandwidth, but the latency to exchange short messages. And unfortunately, just increasing the bandwidth does not guarantee you've improved the latency. People have gotten themselves in real trouble with some information technologies approaches by thinking that more bandwidth automatically equaled less latency. Well, now let's come to the really bad news on the next graphic. This is the bandwidths and latency of us wetwares. How do we stack up with those computers? Well, the latency is pretty easy to specify. It takes about 1/10 of a second for a human being to think about anything and do anything, no matter what you do. This is not very fast. This is a problem. Even worse are our bandwidths. Let me start at the bottom. And you've noticed I've had to extend the scale substantially downward from where I was with the computers. So at the very bottom, we find that keyboard input, if you're very good, you can get about 10 bytes per second. That is a very good typist to get that amount of data in there. With voice input or perhaps mouse input, not so easy to measure, but in general, that's several times faster than keyboard input. Now, if you are reading text, depending on how fast you read, you're up maybe a factor of 10. And of course, lots of people read text on computers. If you look at your hearing ability, that's faster yet, although sometimes it's a little hard to figure out how you make use of that other than by playing music. You do find current computers have a bewildering array of sounds. They can make sounds like animals to warn you that you made a mistake. They can make shrieks and little bells and so forth. It's not clear that huge amounts of information are being conveyed, but they do make the computer a little more interesting to use. Now we finally get to something we humans are good at, which is pattern recognition through the human eyes. Now it turns out, again, this is a little hard to measure, but this covers quite a range, and in fact, the human visual system right now is still better than the best graphic supercomputers we can build, and we build some of the best. Let me give you an example. Suppose you'd like to do an out-the-window driving simulator to test out different designs of cars. We deal with automobile companies all the time. They would like to do this. Suppose they want it to be perfectly faithful simulation of the outside world. The problem is, at the moment, we cannot do that in the fidelity that a person needs who has 20/20 vision. In particular, there aren't enough pixels on the screen to show signs at the distance people can read signs. This is too bad because we would sell a lot of very expensive machines if we could do this. We think it'll probably be somewhere between the year 2001 and 2004 before we can do that to the point where we can fake the human out into thinking they're seeing something real. So this is the good news. Human visual systems are extremely good. In particular, people will notice even a few pixels wrong on the screen. If you've played video games on your home television set, you have probably noticed little twinkling in the backgrounds when you have diagonal lines that have to move around. Fast computers do a technique called anti-aliasing to smooth this out. It's very clear on a television set because it doesn't have very many pixels. But it turns out that even on multiple monitor systems or big displays, humans notice this. And unfortunately, in training people to fly airplanes or drive cars or tanks or whatever, if you're not careful, they will end up being trained to notice these little visual artifacts. And so people spend a lot of hardware to get around this because the human visual systems are very good. Now, our hope is maybe around the year 2001 to 2004, in fact, our graphic supercomputers will catch up. Not that we'll make humans obsolete, but at least will be equal in both the hardware and the wetware. All right, now let's take a look at some more details of how humans interact with computers. So on the next graphic, we have a simple cartoon that shows our prototypical user at the left. Let's look at the human's I/O capabilities. We have very good input through the eyes. We have reasonable input through the ears. We have miserably slow ability to type. That's too bad. Right? And in fact, in many environments, the real bottleneck is being able to get things into the computer. Let's think about how we use our computers to communicate with other users, shown over at the right. Still to this day, an awful lot of communication is done by email, which after all is textual typing and then reading of text on the other end. Now, if you remember the slide a while ago that showed the different rates of performance, typing and reading are really not all that fast. Graphics are better. So now, on the next graphic, let's look at the things you might do to help this human being out. Because after all, you really have to change the computers. In the absence of really serious genetic engineering, human beings are not likely to change very much over these next few decades. So that means we've got to change the computers. Fortunately, the computers are changing pretty quickly. So what might you do? Well, the first thing is look at what's displayed on the computer screen. The more meaningful this is, and the more easily grasped it is by a person, the less time is spent trying to understand what's being displayed. So this means that things like good graphical representations are preferred to just text on the screen. Of course, this can get completely out of hand. If you are faced with a screen that has 20 different flavors of icons you've never seen before, it's not clear that your life has been helped. Nevertheless, it is clear that current computers will use up CPU cycles to give you a more meaningful display on the screen, if for nothing else, so you don't have to type something in just to see some more information. Because if there's one thing to be avoided at all costs, it's the cycle where you type something, see what happens on the screen, think about it, and then type something else. It's that discrete cycle that turns out to go fairly slow. Now, an improvement is to use the kind of thing like when you use a mouse, where you are using continuous motion and watching what's happening on the screen. Turns out that if you can make the response on the screen quick enough, on the order of 1/100th or 1/10th of a second in that range, you can get inside the human's response cycle and the performance can go up dramatically. Now let's do a quick comparison. Suppose that you drove a car the way you type at a computer. So instead of watching out your windshield and continuously changing where you are going, what you would do is see something flash up on your windshield, think about it, and then type turn left at your keyboard. This is probably a bad thing for accident rates. Nevertheless, human beings mostly learn how to drive cars, despite the fact that they are processing more information than the fastest graphic supercomputers can really generate right now. not in a few years. So I think one of the morals here is that anytime you can turn a discrete set of steps into a continuous process that uses the same kind of feedback that a human uses when they're driving a car, you're going to be able to navigate through much more data quicker and in a more sensible fashion. Why is that important? Well, we are drowning in data. Everyone is so excited about the World Wide Web, and with good reason, saying, wow, we will have access to tremendous amounts of data. Sometimes I think the people saying that have not had that kind of access for years, or they would realize that the problem is not having access to the data, it's navigating around and finding it. So this is a real issue we've got to work at, because we're going to have more data just because the disks get bigger. We've got to help the human navigate around in this complex amount of data. The other thing we might do is put a video camera on top of the machine with the hope that you can use video conferencing or take a video of a quick description and then email it to somebody. After all, anytime you can turn a lot of text typing and reading into graphical representation, this is a good thing. Now, on the next graphic, let's go on and look at the time variance in how fast a response you can get from your computer. So once again, we have another of these logarithmic scale charts vertically. This is the number of seconds to get a particular kind of response from a computer. The horizontal scale means the date. That is, over time, any given function gets faster and faster. So if you start at the upper left and you look at some process, you discover that faster computers make that process faster. Now, most people don't think of programs that run several weeks or a month, which is the upper left corner. Nevertheless, we have plenty of customers at Silicon Graphics who run very, very long-running jobs like that, always in the background of their workstation, and they run it for months to get some answers. I've spoken to many customers like this. They, of course, would prefer that it would be faster. Of course, if it would faster, they would just run bigger jobs and it would run longer again anyway. Now, if you look at what people do when things get faster, the next thing that happens is that you get something that works overnight in a batch mode. This is not so bad. About the time you're ready to go home, you submit a job to some queue. It sooner or later runs. You have the results back the next day. Many people who do chip design or mechanical computer-aided design use this kind of technique for long jobs. Now, when the time gets down to, say, 10 seconds or 20 seconds, you'll sit there and you'll wait for it to come back. This is the kind of run and look scenario that you often see people do with spreadsheets that have graphics outputs attached to them. That is, you'll change a number, you'll see how the graph changes. You'll change a number, you'll see how it changes. It still could be the same program you were using for the batch version, but it's fast enough you will not go to some other activity. Now, when the real magic happens is when you get the time down, typically under 1/10 of a second, maybe closer to 1/100th of a second. At this point, the program mutates into a program that truly expects the human being to be there steering it. Let me give you the kind of thing that's happened. Quite a few years ago, I used to do 2D graphics on these old CalComp plotter machines. You submitted a job, it ran overnight, and it came back with a plot. If you goofed, you would discover a diagonal line through the plot where you forgot to raise the pen. You would kick yourself and you'd submit another job. This was really not a lot of fun, and not very many people did this. On the other hand, almost any user of a personal computer these days or workstation has some kind of drawing program that will let them quickly put things up on the screen and interact with them. It's a very different kind of program because it expects that as you move a mouse around, that graphical objects on the screen will be rubber banded and stretched and shrunk. It expects the human being to be there giving immediate feedback. You can do this surprisingly quickly. And of course, that's the simple case. If you look at the kinds of programs there are now, you find wonderful composition programs for making beautiful graphics in various forms. Now, 2D graphics has mostly gotten to the point where it's interactive. Once this kind of program gets to be fast enough that making it faster only means that the computer's idling faster, you might as well not make it any faster. What you tend to do is make it cheaper. And in fact, then, once you get to that level of capability, you keep making things cheaper and cheaper. You hope you don't get to the point where you sell an infinite number of things that cost nothing, because you don't make very much money that way. Now, the 3D world in the last 10 years has started to get into this same interactive position. The difference with 3D is that the ability to really show what you want on the screen can rapidly increase to consume any amount of CPU power that you've got. That is, you tend to run models with more polygons, more computing to be able to show you the model in the form you want. So it appears that this market tends to soak up almost any amount of compute and graphics power you can do. And in fact, there are large science and engineering applications that we are many, many years away from being able to do the kinds of things that our customers can imagine. This is actually a lot of fun to talk to people who say, this is what we need. When can you do that? And the answer is maybe 10 years from now. And they say, well, we'll start with what you've got now, but we really want that next thing. In this next graphic, we see the way that families of computers evolve to give you that better performance every few years. In this graphic, we see a family of systems ranging from a small desktop at the lower right to a refrigerator-sized box on the upper left. That's what most people's computer product families look like. They're seldom bigger than refrigerators because it's considered good form to get them into elevators. Building computer rooms around computers is not considered good form. What happens is that each new generation of computers, the performance and capacity of the biggest one moves down to the next smaller one, and its performance moves down till it goes onto the small desktop, or even off the desktop onto a television set. So let's take a look at how this has happened several times. In the next graphic, we see the Silicon Graphics computer systems product line a few years ago, around 1988-89. At the high end was a system with 8 R3000 CPUs costing several $100,000. Now, in just a few years, by around 1993, 1994, in the next graphic, we see that the big machine has boosted itself to have up to 36 CPUs, and they are faster ones. And in fact, the performance of that large original machine actually can be found on the Power Desktop machine in the middle of the product line. And the performance of a number of those R3000s is incorporated in the low-end desktop at the lower right. So if you arrange your software so that the same binary programs run from one end to the other, what happens is that a customer can start with a big machine, develop some software that in fact is too expensive to run on affordable machines that you can put everywhere, but knowing within a few years that level of performance will be widely distributable and affordable for people. So on the next graphic, we see in fact the specific examples from Silicon Graphics history. This shows high, medium, and low. That is, high-end machines go for all-out performance. The mid-range machines go for price performance and a range of graphics performance. And the low end has to get to a certain price point. Each generation, the performance moves down from the upper left down to the lower right. We usually try out the new features and new performance in the high-end machines first, learn how to do it correctly, and then move that performance down. Now, one thing you would not want to do is seen in the next graphic. That is a screen full of black and white numbers. You notice this is crossed out. In particular, the Silicon Graphics logo is carefully scratched out because we would get rid of any machine that dared show us a screen like this. This is not good for you. What do you need instead? Well, let's take a look at that. On the next graphic, we see the kinds of customers that we end up dealing with. They're very often people with a lot of data coming at them, people like scientists and market researchers. Or they have to create and modify and control a great deal of data. These could be people designing airplanes or cars or creating movies and animation. But in all of the cases, people need to turn their data into information and even better, insight. And then they have to communicate it to other people. This is not just having the data. This is not doing word processing necessarily. This is pushing a great deal of data around and making sense out of it. And it has a different set of requirements than you find for the kinds of computers that everybody uses. What do you need to do? Well, there's 6 kinds of technology and expertise that turn out to be necessary. Of course, you need fast graphics because that's how human beings acquire information quickly. You need fast CPUs. In our case, we like CPU chips that mix 64 and 32-bit processing so they can address that huge amount of data that's now available. No matter how fast you make a single CPU, there are customers who want more, always more. So you'd better do scalable, symmetric, shared memory multiprocessing. We, of course, do that. To make data make more sense to people, you want to support digital media, that is, audio, video, image. You need to support those well because, frankly, that's the way human beings acquire information. Now, in all cases, you have to think hard about how you organize the information and show it. I'm going to come back to this one later. We sometimes call this high-leverage human interfacing or advanced human interfaces. It's the software models that let people create better images in the computers and who let them extract information from the data that they have. Now, the last one is one that's hidden. That is, big I/O and networking is the ability to move the data around quickly. Everybody knows about CPU benchmarks. People quote all kinds of graphics benchmarks. What's often not something that gets so much credit is the ability to move the data in and out of the machines quickly. Nevertheless, a great many systems fall down if they are not good at this particular part of the equation. Okay, so now let's take a look at the kinds of application software that people do that fall into these categories here. In the next graphic, we talk about the traditional high-end markets. That is, people who always want more. I love these customers. They are never satisfied with anything. If you satisfy their needs, they come back with a requirement that wants more. Well, they understand you get 4x every 3 years, and they want to use it. These are people who, for instance, do visual simulation, where you're trying to simulate the effect of the real world, like driving a car, flying an airplane, steering a tank, or steering an oil tanker. You know, it's considered a good idea not to crash oil tankers into cities. So there are people who do training simulators that try to simulate real-world ports like Rotterdam Harbor, for instance, and train the boat pilots so they don't crash into things. It's very expensive to crash into things. Much cheaper to buy a powerful computer and get it right in the first place. Another thing where it's good to get it right in the first place is architectural design. Most people do not read blueprints very well. They'd much rather look at a picture of the building. This is why architects often do renderings, to give you a flavor for the building. Quite a few new buildings are being built by making a model in the computer, letting a person walk through it, make suggestions, change the lighting. Lighting models are very hard to get right. Try to get the building right beforehand. A similar area is mechanical engineering or mechanical computer-aided engineering, MCAT. This is about 30% of Silicon Graphics markets. People build airplanes, they build cars, they build boats, they build all kinds of things, including toys, that you might not expect, by putting the design into the computer, looking at it, exchanging information much quicker than writing text to describe what the toys or products are going to look like. Scientific research, of course, has always had huge amounts of data, where the whole purpose is to gain insight about what's happening. Same sort of thing happens in geological sciences, the oil and gas industry. The insight you want turns into money. Where shall we drill or mine? Another area that's widely used is computational fluid dynamics, which starts with looking at the airflow over wings of airplanes or around cars, but turns up in as odd places as the design of chocolate ice cream bars. Well, you know, ice cream melts when the hot chocolate comes. They want to optimize the shape to minimize the melted ice cream so they don't have to clean out the machine so often. Another important area for computational fluid dynamics is baby diaper design, which is definitely a fluid flow problem. Now, an area that people know we do a great deal with is computer animation and computer-generated effects. Everybody's seen Jurassic Park and similar things. That's only about 15% of what we do, but it's so visible, unlike some of these other things, that people always think of that. In fact, this last one here, medical imaging, is an area that actually uses some of the same technology as these other things, and of course may well save your life someday. In fact, that's one of the odd things about these. Most people who use computers do not do these activities. Nevertheless, that these things go quickly, or that people reach solutions like new drugs done by chemical modeling, right, may very well affect your life or your children's life. Nevertheless, you won't see the computers that do it. Of course, I have to point out a number of these are silicon graphics machines. These are the people we talk to. These people always want more. Now, let's look at the next graphic. Things that don't necessarily always need more, but get better when you can apply the same techniques. And I'll go through a few of these. Unlike the previous ones, where frankly I have trouble getting the good images onto videotape, these are a little easier. So let's look at a couple of the applications where these aggressive human interface techniques are being applied to tasks that more people do. So on the next graphic, we see digital media publishing. In fact, this was the program that we used to make these slides. It's nice to have graphics, image, video, audio, all incorporated into a presentation. On the next graphic, we see something that more people are becoming familiar with. This is called hypertext. This is collections of text, often including graphics and images, that you can navigate through to find your error messages or your training. It saves an awful lot of bookshelf space to have this on CD-ROMs instead. Now, this, of course, in its more ultimate extent, is the World Wide Web. In this case, we not only have digital media publishing and hypertext and hyperlinks, it goes worldwide. People can log in from anywhere, look at web pages. The web, in just a few short years, has turned a giant mass of text into graphic images that people can see, get excited about, follow around, and create for other people. Now, if only things moved so quickly on the next graphic, that is, computer-aided software engineering. It's sad but true that there are many case environments that are simply GUI interfaces laid on top of 20-year-old tools. Why do I say 20-year-old tools? Well, I've recognized some that were written between my office and the one next door 20 years ago at Bell Labs. And unfortunately, human beings don't process any more text tokens per minute than they used to. So it's not clear that just putting a GUI interface really helps you very much. Now, we and various other vendors are working very hard to show multiple, often graphic representations of programs to help a human understand them. Problem is, Parkinson's law works here also, is that the complexity of programs expands to fit what a human being can manage, and no further, because then the programs break down. So in fact, if you look at the next graphic, you discover some of the current trends in computing include things like more graphics, parallel processing, digital media, object-oriented techniques, all kinds of things that people have to worry about. Anytime you do digital media, you get into real-time problems, because human beings are very sensitive to the smooth flow of information on the screen. They notice jerkiness. In fact, in the bad cases, certain kinds of virtual reality environments, if they're jerky, will make people sick. This is not good. So these are issues that people did not worry about so much 20 years ago. Now, how can we improve things? Well, the best improvement is to not write programs at all. Example of that is shown on the next graphic. This was a program called Explorer. It's a toolkit that a scientist or engineer plugs together to process their data without ever writing any code. You do it graphically, the data flows in the front end and comes out the back in a nice graphic. This is a big help because you can get a look at your data without having to write a program. Same sort of thing happens in the next graphic. Here we're getting further and further away from portrayal of the real world into having good graphic representations of things that don't have any physical existence. This particular example is a set of telephone trouble reports from one of the large telephone companies where you can manipulate the graph at the bottom with a slider bar, and you will see the time of day or other attributes, and the bars on the chart will move around. It's surprising how sensitive human beings are to small changes of relative motion. Those changes really highlight oddities of the data that can help you focus on problem areas or things you need to look at. Now that brings me to one last example. In fact, most of you have actually already seen this program. This illustrates flying around through your data in a 3D space, almost like a data helicopter. You can hold the mouse button down and sort of cruise over your data. In this case, it's a map of your disk space. It could be a map of the sales of your company. It could be other kinds of data. Or you can point at a place out in the distance in this 3D environment and immediately fly over there. When I say you've already seen this, let me give you the example. In the movie Jurassic Park, you may recall the very tense scene in the control room when the dinosaurs were banging at the door for lunch and the human beings preferred not to participate. Hence, they were looking for the lock for the door. The little girl went to the workstation, said, Unix, I know this, proving she was a typical average kid, and immediately flew through the representation of the park, found the lock, and locked the door before the dinosaurs could obtain lunch. This, of course, proves that good visualization and 3D graphics can protect you from hungry dinosaurs. That brings me to the final conclusion. Let's recap this, thinking that we have three sets of trends. The first trend is in hardware. We see 4x every 3 years kinds of capacity and performance increases. So the hardware vector keeps going up to the right, and I think it will for quite a few years yet. The second vector is horizontal. We really do not expect that the fundamental characteristics of humans is going to change very much in the next few years. Now, that doesn't mean that humans cannot increase their performance by learning and getting accustomed to different techniques. It just says that the fundamental characteristics of people have gotten there over a long time and are not about to change very quickly. So that brings me to the last piece, which is the software vector. Software is what has to fill the gap in between. And the exciting thing about this to me is that while hardware and wetware seem to be fairly predictable, software is just filled with surprises. We do things now that I never would have dreamed of just a few years ago. People come up with better ways to suddenly get much more data into the computer in a form that the human can manage. Or they figure out ways to extract more information from the computer and make it something that communicates to the human beings. So those are the three pieces of the computer business: hardware increasing, wetware not, and software full of very exciting surprises over the next decade or so. Thanks very much for coming. I hope you enjoyed this talk and that it makes you think about some of the possibilities we'll see in the next few years.